Good morning, everyone, and welcome to Earth Science Week, October, also known as Rocktober. I'm very excited to have you all here again. Someone's just popped in the chat. Yes, this will be recorded, and we will send all of the recordings tomorrow with the follow-up notes from each of the presenters as well. So if you do have to drop out or want to watch something again that you were really interested in, with no problems, we'll have those recordings available for you as well. So we started off this morning with Geoscience Australia with a fabulous look at meaningful minerals and rocks. And today we now have Amelia from Fizzics Education, who's going to talk about the rock cycle and some of those geological features. We're very proud that Geoscience Australia is supporting us today to enable us to do all of these programs for free for Earth Science Week. So a big thank you to them. And I'm going to hand straight over to Amelia from Geoscience Australia, from Fizzics Education for our wonderful session for this morning. Thank you very much.
All right, thanks Karen. So hi guys, my name's Amelia, as Karen introduced me. I'm from a place called Fizzics Education. We're based in Sydney. So I can see lots of participants today. Hands up if you're in Sydney right now. I want to have a look. Now guys, I'm sure you're used to the webinar format, but if you're not sure, I can't see or hear you, but you can see and hear me, but we can still interact. I have got my question, the Q&A and the chat live on my other screen. Now personally, I prefer if you type in the Q&A. So if you look at the bottom of your screen there, use the Q&A, and then I can see that live on my screen. If you have questions at any time, then send it through the Q&A, and I'll also ask you lots of questions a lot. Now, we go to lots of different places, do lots of different kinds of science, but yes, it is Rocktober, and personally, I think geology rocks. Get it? Get it? Well, yeah, I actually love geology. My favorite kind of science is paleontology, which is a mixture of geology and biology together. Now, in my session, we're going to kind of learn a bit more about different rocks, different minerals, the rock cycle, and all sorts of other things like that as well. Now, I think before you did something about minerals, I'm wondering if you learned about different sorts of rocks and minerals. Does anyone know the difference between a rock and a mineral? If you do, type it in the Q&A because I want to see if you learned about that. I have a way that I like to remember it as well, okay? So a rock, it's kind of like lots of minerals stuck together. A rock can be made up of lots of minerals. If you imagine a chocolate chip cookie, well then the chocolate chip cookie itself is like a rock, but all the stuff inside the rock would be the minerals, like the chocolate chips, the butter, the flour, stuff like that. That would be the minerals. Oh, and now I can already see some people are preempting some kind of questions I'm going to ask. Guys, there are 3 main categories of rocks. If you know, tell me in the chat or the Q&A. I can also see my friend Grace has already told me all 3. Now, I want to start learning about them a little bit more in depth. I have some rocks over here, and I want to think about the first type. Oh, I've got another person in the Q&A saying sedimentary. Yep, that's the first type I was going to think of. Yes, excellent work, Charles. They're giving me all 3. Let's start thinking about sedimentary. Here's an example of a sedimentary rock. I wonder if you actually know what sort of rock this is. There was a bunch of you that were from Sydney. If you're from Sydney, you probably know what this rock is because Sydney has a heap of this rock all around. So if you know what it is, type in the Q&A. Let me zoom up on this rock as well. Now, one way you can tell it's sedimentary, can you see all those layers? Layers and layers and layers. That's how we get sedimentary rocks. The word sedimentary sounds like sediment. So a lot of our sedimentary rocks come from sediment, little particles, dust, mud, stuff like that, layering on top of each other, on top of each other, on top of each other. They get pressed with the pressure of the earth and turn into a rock. Let's see if anyone knows what sort of rock this is. Oh yes, I got a bunch of people saying the correct name. This rock is sandstone. And if I rub it kind of hard, well, I don't want to rub it too hard to break it, but there's actually little crumbs of sand coming off. Now, as I said, I'm in Sydney, and so are lots of you. Sydney is inside this big sort of basin filled with sandstone. We have heaps of sandstone, and all this sandstone was made millions of years ago before the dinosaurs in a period called the Permian period. So lots of sand was deposited, and then it got squished over time and turned into sandstone. Now, if you're thinking, well, what's sandstone made out of? I mean, it's kind of easy. It's made out of sand. There's a few other kinds of sedimentary rocks named that way as well. We have mudstone. What do you think that's made of? Mud. Siltstone, that's made of silt. So some of them are really sort of simple and easy to realize what they're made out of. Now, remember I said before that I really like paleontology. Inside sedimentary rocks, this is the kind of rock that you're most likely to find fossils. Because if you imagine, if it's through layers and layers and layers, a fossil animal or plant could easily squeeze in there, get pressed by the pressure of the earth and turn to a fossil over a long period of time. It's important to notice these layers on sedimentary rocks, and this sandstone showcases it beautifully. Okay, talked a bit about sedimentary rocks. Who knows another category? There is a bunch of people who are saying the correct ones. The next one I want to talk about is igneous rocks. Now, there's two categories we haven't talked about. Who can actually define an igneous rock? What is an igneous rock? And I have another way that you can easily remember the different types as well. So remember, sedimentary sounds like the word sediment. Sediment is like sand and mud and silt that you find on the bottom of rivers. That's one common way that they get made, from sediment on liquid areas. Who knows what an igneous rock is? Oh, let's see. Yep, Tom, Will, and Sam, created by lava and magma. Absolutely. And the way I like to remember it is igneous sounds like the word ignite. So ignite, like set on fire, like a volcano. That's how I remember igneous. Now, I have a few igneous rocks as well. Let me zoom up again. Here's a small one in my hand. These are smooth and shiny. I wonder if anyone actually knows what these are. So it has like a proper name. Some people call it volcanic glass. I'm wondering if anyone can tell me what sort of rock this is. Let's see. Oh, I dropped it. Now I've got to be careful because, as I said, it is volcanic glass, so I don't want to actually splinter it. I wonder if anyone has told me the answer. Let's have a look. Yep, lots of you know it. This is totally obsidian. Now I'm going to open up the participants list again, and I want you to put up your hand if you've ever played Minecraft. Who's ever played Minecraft? Me? Oh, yeah, I can see a bunch of you with your hands up. Excellent. Now, guys, can't you get obsidian in Minecraft? How do you get obsidian in Minecraft? Tell me in the Q&A. How do you get obsidian in Minecraft? Don't worry, this relates to science in some way, okay? In Minecraft, how do you get obsidian? This beautiful, black, shiny... Oh, lots of people are telling me water and lava. Absolutely, guys, guess one way you get obsidian in real life? Water and lava. You get obsidian when it cools really, really, really fast. It doesn't have any time to grow big, long crystals like other igneous rocks. Now, I do have another one here. You know, if you're looking at my table, you can see two big rocks. I've got my sandstone, then I have this giant one. Who knows what this rock is? This is another igneous rock. It looks completely different to the obsidian, though. Something completely different. Let's have a look. Anyone know? Not granite. Now that's a good one. That's another igneous rock, okay? Oh, lots of you have got the correct answer. Oh, it's not a geode, though. If I were to crack open a geode, you'd find some crystals inside, another sort of igneous rock. But guys, this is actually pumice. Now, this rock looks really, really big, and I'm not really feeling that strong today, so I'm going to have to try my hardest to lift it up. Let's see. Oh, it's so heavy, guys. I wish one of you was here to help me. Wait, hang on. Wait a second. Wait a second. Guys. Well, I was just doing a little joke, but this pumice is actually super light. This is a huge rock and I'm handling it easily, just with one hand. In fact, this pumice can float on water, and I'm going to prove it to you. I actually have a tub of water over here, and I'm going to prove that this entire big rock can float. This is just regular water from the tap. Could you believe that a rock can float in water? Check that out. This giant rock is floating entirely in water. That's because the pumice is filled with air. It's kind of like a crunchy chocolate bar or a violet crumble, you know, when you bite inside those and the honeycomb has got or full of air pockets. That's pretty much what the pumice is like as well. So that pumice is filled with air and it can float on water. Now I'm going to take the pumice out because it can float, it's full of air pockets. Sometimes the water sneaks in and then it will end up smelling like stinky water if I let it soak too much. But that's showing you how that pumice can float on water. Now the obsidian is formed by lava cooling really, really fast, but the pumice is formed by cooling as well really fast, but in a different sort of manner. Instead of touching cold water or air, it sort of gets ejected from a volcanic eruption up into the air, and then the air pockets cool inside it as it cools as well. So that's how we get another type of our igneous rock. Now, some igneous rocks will cool very slowly over time. Now, when we think of lava and magma, who knows the difference between lava and magma? Now, I can tell my camera is a little bit blurry. Let's just do some refocusing forward and back. That should help. Who knows the difference between lava and magma? Oh, I can see a few of you live reacting in the Q&A telling me that they were very impressed by that floating pumice. Now, guys, you probably actually have seen pumice before because maybe you've noticed some people have a pumice stone in their shower. They use it to scrub the bottom of their feet. Ew! But you can just buy pumice from the chemist. So maybe you can have a look and see if you've got real pumice available. Now, my friends are saying lava is a liquid, absolutely, but magma is also a liquid. So some of you are saying magma is solid. Not quite. Lava and magma are both liquids. Some are saying lava is more liquidy. Not quite either. So lava and magma can have different viscosities. Ooh, that's a big word. Viscosities pretty much just means goopiness. Oh, a bunch of you got the right answer though. Magma is under the ground and lava is when it comes out of the ground. Yes, excellent work, excellent work. Oh, by the way, one of my friends says go to the beach to get pumice. That's exactly right. I was going to give you a little bit of homework. Well, it's summer coming up, the weather's getting pretty warm, so next time you go to the beach, just have a look on the sand, you know, where the tide comes up and it deposits all the seaweed and rocks and weird things. Sometimes you can find little bits of pumice. But it came from a volcano. How did the pumice get all the way to Australian beach? Honestly, if a volcano erupted near Sydney, I think we would know. I think we would hear about it on the news. So I found pumice just on Bondi or Manly Beach in Sydney. You can find pumice on all beaches all down Australia's coast. Where does it come from then? Who can tell me? Let me know. I'm having a look. And don't forget to ask questions as well. I've got my chat and the Q&A open, so hopefully I won't miss it. Oh, ocean currents. Yes, exactly. So it floats from other countries on the currents. Absolutely. If there's a volcanic eruption somewhere else, because the pumice can float, it'll get deposited on the beach. So that's your homework. I'm not going to check it, but next time you go to the beach, try and find some pumice. Okay, we've talked about sedimentary. We talked about igneous. We've got our lava that comes out of a volcano or when it's just out of the earth. Magma is inside the earth. We can get igneous rocks from magma cooling really slowly. That's when we get our really big sort of crystals and geodes. And then the last category, lots of you have told me already, it is metamorphic. Now, a way you can remember metamorphic is, it sounds like the word metamorphosis. Now, that's a big long word as well, but maybe you've heard of it before in regards to animals. So a caterpillar turns into a butterfly. That's known as metamorphosis. Metamorphic rocks are rocks that change over time, usually due to heat or pressure. Now, I have a little one here. Let's zoom up. Because it looks kind of like a sedimentary rock at first. It probably was a sedimentary rock at one point. Oh, I wonder if you can see, there's actually some layers there, but the layers are sort of bent and warped. It's kind of like when you leave a chocolate bar in the car. It doesn't melt fully, but you're able to bend the hard chocolate into like a sort of just a rounder shape you can bend, and it's very slowly, easy, malleable. That's showing you how the metamorphic rock has changed simply due to heat and pressure over time. Now, a common metamorphic rock you may have heard of is actually marble. Maybe you have a marble countertop in your house, or maybe you go to a fancy hotel and they have marble pillars. Marble is limestone, which is a sort of sedimentary rock, that's been changed over time with heat and pressure. You can actually sometimes very rarely find changed fossils inside marble as well. So we have sedimentary, igneous, and metamorphic. Now I have a couple of other rocks and minerals I want to show you before we move on. And the first one is this very pretty one here. Who actually knows what this one is? It's very sparkly. And you know what? I might actually change to a different camera. I have a top-down camera as well. Let's see. Over here, yep, coming over to the other side, we can look at some rocks and minerals up close. That's our shiny obsidian. And here's another shiny sparkly mineral. I'll leave that there. Who has correctly identified this mineral? Let's have a look. Ooh, it's not silver. Ooh, I can see lots of you actually have the correct answer. This is pyrite. Now, it looks very beautiful and sparkly, and if I found this, I'd be like, wow, I'm rich, but it's actually not that worth, it's not worth that much, okay? It's one of its nicknames is Fool's Gold because people think it looks like gold. But this is actually made from iron. I still think it's very beautiful. Here's a couple more rocks I want to look at. Now, these ones look pretty much exactly the same, but one of them is magnetic. And I wonder if we can figure out which one is the magnetic one. So if I move this around, I mean, the compass needle's still moving a little bit. What if I get the other one? Ooh, okay. Yeah, guys, I'm pretty sure this one over here is totally magnetic. This is magnetite. Well, I can see my friends saying hematite is magnetic as well. Excellent. Now, we'll talk more about this in a minute when I show you the insides of the earth. I just want to show you one last way we can look at rocks and minerals. Some rocks can actually glow under UV light. So here's some rocks there. That's what they look like just in regular light. Now I'm going to turn off the big light. Ooh, it's a little bit spooky. I do have a UV light off to the side. So let's investigate how the rocks change with some UV light. This one originally was orange. Now it's actually glowing, sort of a bright green. I can see a stripe fluorescing in there too. Over here, this one starts to glow a lot more. I'm going to hold it a bit further away, but these two on the side, you should be able to identify little orangey patches that start to glow. Oh, that one is definitely glowing. And another over here. There's little patches inside that are fluorescing under UV light. I have one more, a little small one here. This one also glows. Let's see if I can get the right angle there. This one is a semi-precious stone. I wonder if anyone actually knows what it could be. I'll give you a hint. It's actually the birthstone in October. So if you're born in October, then you're really cool, just like me, because that's where my birthday is. So here's the semi-precious stone. Often it's polished and it can be made into jewelry. And it's really, Australia makes really, really good kinds of this sort of mineral, especially in South Australia. Let's have a look. Yes, this is opal. Excellent work, guys. That is some opal. And opal actually fluoresces under UV light as well. So if your parents have some opal jewelry at home, and if you have a UV light, if with their permission, of course, maybe you can investigate to see if the opal fluoresces. Okay. We've talked a bit about the different categories of rocks, but guys, I want to talk about how these categories of rocks interact. That's what the rock cycle is all about. Rocks can be created and destroyed, and it's kind of in a big cycle with our different categories. And to think about this, we actually got to think about our Earth as well. Now, this is one hemisphere of the Earth, the southern hemisphere. Got little Australia there, and I'm going to show you the insides. Who actually knows the different layers of the earth? So write in the Q&A for me. I love to ask you guys questions because I get super impressed when you have all the answers. Let's have a look. Now, if you look really closely, maybe you can read the labels, but I can't read it from here, so I'm hoping that's not cheating. Who knows any of the layers of the insides of the earth? I'll move my sandstone over to the corner because I'm going to bring this model into the middle as well. Oh, this might help. Who knows some layers of the earth? Oh, excellent. I've got a bunch of you saying all of the layers for me. Fantastic. Let's talk about one of them. I want to talk about the crust at first. So the crust is going to be this blue one. It's really, really thin. And that's pretty much all that humans have actually actively explored. That's the crust. And on this larger model, the crust luckily is also colored blue, this blue layer at the top there. Now, when I think about the insides of the earth, I get a bit hungry. I mean, I've already talked about cookies and chocolate and crunchy bars, but the insides of the earth kind of remind me of a pie because it's got that flaky crust on the outside. The crust isn't all connected. It's actually got like little flaky pieces to it. Does anyone know what those pieces are called? What are the pieces of the crust called? And underneath the crust, there is that warm, gooey pie center. That is the mantle. That's where we're going to get all our magma. So that's how I remember. Magma, mantle. That's where all our sort of liquefied rock is hanging out. Now we go further inside the earth. It's still liquid in the outer core. That's that big red part. This is made mainly of iron and some other rare metals as well, but lots of it is iron. And then in the middle, it's like that part that when you microwave the pie, it just gets really, really hot in the middle for some reason. That is the inner core, and that's actually a solid because it's getting squished by the pressure of the earth. That's a solid, and in some places it's even hotter than some areas of the surface of the sun, thousands of degrees Celsius. Now let's have a look at my question and answers to see who has answered my question. Yes, the flaky parts of the crust are called tectonic plates. And yes, a few of my friends are also saying they're getting hungry, talking about geology. Yeah, I know, me too. Okay, it's probably going to be lunchtime after this. Now, this spinning, the outer core and the inner core are actually spinning around. And that's how we get Earth's magnetic field. If you remember the compass and the magnetite before, those magnetic rocks, they are made of iron and they actually preserve the Earth's magnetic field inside them. Now, with the mantle, this is how we get our tectonic plates moving around. Because I'm sure you've heard this before, but did all the countries look exactly the same as they did millions of years ago? No, actually, they have moved around over millions and millions and millions of years. A long time ago, before the dinosaurs, there was an ancient supercontinent called Pangaea. Pan means all, so that's all of the continents stuck together, and on the other side of the earth was just a plain ocean. That was called Panthalassa. Thalassa means like water, ocean, so all ocean. Once you learn a little bit of Greek and Latin, sometimes it's easy to figure out what big long words mean. Now over time, these tectonic plates moved around. It's all because of the heat inside the mantle, something called a convection current. Basically, simply, hot stuff goes up and cold stuff goes down. If you think about boiling the kettle for a cup of tea and steam is coming out, that steam is going to be rising up, okay? Hot stuff goes up, cold stuff goes down in general. So the core is super duper hot. The mantle next to the core gets heated up a lot, then it rises towards the crust, and then it starts to cool down because it's close to the top of the earth. And so that cold stuff goes down, then it gets warmed up again, so it goes up, and then it goes down, and then it goes up and goes down, and that's what's forming convection currents. And this is how the tectonic plates slide around through the crust because of these convection currents. There's convection currents in other places, like in the air, that's how we get lots of weather. In the oven, that's how you can cook some yummy food. See, more food talk. Now, let's think more about these tectonic plates. I have a few I want to show you. Well, actually, how about I just share my screen? I have a little screen here, and I want to show you some common ones. Let's have a look. Let's see. There we go. Looking for my share screen button. 1 second, my friends. I am thinking about the different tectonic plates, and I actually have a map that might look a bit different to what you normally expect. All right, guys. Here's my tectonic plate map. Just let me know if you can't see it. But this is still the map of the Earth. Don't you normally see it with all the countries in the middle and then the Pacific Ocean off to the side? This is still a map of the Earth. It's just a little bit of a different perspective than what we're used to. We've got Australia over here. We've got the Eurasian plate. This time the Eurasian plate is cut in half. Normally the Pacific Ocean is cut in half. We have a whole bunch of different plates. And if you observe, these red arrows actually show the direction that they're moving. Now, the reason why we chose this map is because this plate here, the Pacific plate, is the biggest one. Now, guys, I know it might not look like the biggest one on screen, but that's all because the Earth is round, okay? And when you get a round shape and flatten it out onto a rectangle map, it distorts the top and the bottom. So that's why the top and the bottom look giant. In fact, have a look at how big Antarctica is. Guys, it is not that big in real life. It's just a distortion of the map. The Pacific plate is definitely the biggest one. And if you have a look on the outside here, that's called the Ring of Fire. We actually get a bunch of volcanoes in this area. Don't worry, we'll talk more about volcanoes and tectonic activity very soon. Now, let's have a look again. This is showing our Ring of Fire even more closely. And here, well, here's Australia. Can you guys see our friendly neighbor over here? That is poor old New Zealand. New Zealand is right in the middle of a tectonic plate boundary that's smashing into each other. I'm sure you've heard that New Zealand actually has lots of earthquakes. Australia definitely does get earthquakes sometimes, okay? But really not to the same degree as New Zealand would. And that's because of our position. Check it out. Australia is right in the middle of a tectonic plate. New Zealand is cut in half. Now over here, this is the Indian plate pushing up into the rest of Asia. And guess what's found over here? This is where we find the Himalayas, the tallest mountain on Earth, Mount Everest. All right, I'll stop the share there. I want to show you some more tectonic plates, and I've got actually a giant puzzle over here. I only grabbed a few pieces. Let's have a look at Australia again. As I said, Australia is in the middle, so we're not going to have a lot of tectonic activity. These tectonic plates can slip and slide and go into each other. That's part of how our rock cycle is formed as well. Now, with the tectonic plates, they actually move about as fast as your fingernails grow. So next time you trim your fingernails, you can imagine that the tectonic plates have moved, although Australia's plate is moving even faster than that. We're actually kind of winning. We're going northwards really, really super duper fast. I wonder what it will look like in a few million years. Another one I wanted to show you was South America and Africa. Because if you observe this here, that's showing the Atlantic Ocean in the middle. But if you use some imagination, you can kind of see how Brazil would fit right into the coast of Africa. Maybe for an activity, you can get a map of the world that has a tectonic plate on it, and then you can cut out the continents and try and mix them up and put them together like a puzzle, what ancient Pangaea would have looked like. So that's the basics of how our tectonic plates move around. They're sitting on top of the mantle with the convection currents, and that lets it slide around and how we get some movement. Now, there's different ways that the plates can interact with each other. Sometimes they crash into each other like this. They have a lot of energy, and it's building up, building up, building up. That's going to make our mountains. Some volcanoes as well, but usually mountains. Sometimes they meet, and then one is a bit more dense than the other, and it goes underneath. Usually the oceanic crust is more dense than continental crust. So the one with the oceans on top is heavier than the one with the countries on top. This is called a subduction zone. And on my model, you can see one pretty clearly here. As this blue part goes down, then that shows the subduction zone. And here, that's a volcano building up. It's from all the inflammation of the earth in the subduction zone. Sometimes tectonic plates meet and they sort of slip and slide past each other. That's when we're going to get lots of earthquakes. That's called a transform boundary. And then sometimes they're meeting, but they're actually not crashing into each other. They are ripping apart in a rift valley. That's what's in the Atlantic Ocean, and there's some on top of the earth as well that you can find like in Iceland or East African Rift Valley as well. All right, guys, I'm just heading back to see the chat or the Q&A if anyone has added some extra questions or answers for me. Nope, that's okay. Don't forget, you can always ask me some questions. Now, with the rock cycle, don't worry, we're getting there. It's all about how those tectonic plates interact with the different continental crust, because if you think about it, sedimentary rocks made from sediment, that's made from other rocks that have been eroded away. Maybe they've been washed by water or with air, or they've been smashed, or there's an earthquake and something's happened. Lots of rocks crumble, crumble, crumble. Then over time, they turn into a sedimentary rock. When we have our subduction zone, if there's a continental crust, that's going to go underneath the earth and get absorbed back into the mantle. Well, then the mantle would come out of a volcano, and then that's going to form into an igneous rock. Then over time, that can be changed into a metamorphic rock just with some more heat and more pressure. So it's a giant cycle. New rocks are getting created all the time, such as in our rift valleys. As they move apart, the magma comes up and then turns into a rock as well. So that's how we have our rock cycle. Now, I also want to think about some soil. So one of the questions over here was, how is sand made? Now, most of our sand is made up from like silica-based rocks. It's essentially just crushed rocks over a long period of time. We have so much sand on our earth. Well, that's because we have a lot of rocks as well. It gets washed away through rivers down into the ocean, and then over time, it'll be reabsorbed back into the earth. Now, when I say over time, I don't mean just a few days. This stuff takes millions of years. So if it's hard to imagine how a mountain can be formed, well, just remember that it takes so long. Humans aren't really able to see it in real time. We've got to use some imagination and theories to figure out how this stuff works. It takes millions and millions and millions of years, just like how fossils take millions and millions and millions of years. Now, I'm having a look over here as well. Oh, what a great question, Charlie. Why does Brisbane have a lot of metamorphic rock? Now, I'm not an expert in Brisbane's geology, but I'm just imagining, where's my little Australia map gone? Brisbane, up north, Australia actually does have volcanoes. Pretty much all of them are extinct, but down the east coast of Australia, we have something called the Great Dividing Range, and those used to be very active volcanoes. So long ago, when Australia was joined to Antarctica and the rest of the Gondwanan continents, so these are after it broke up, after Pangaea, Australia had to move northwards up from the South Pole to where its position is today. Now, this kind of reminds me of what's going on over here. We can get hot spots underneath the tectonic plates that kind of bloom up, and then on top of that hotspot, a volcano forms. If there was a hotspot just around here or anywhere along Australia's east coast, as this Australian continent was moving northwards, more volcanoes were created over time, and that's why we have the Great Dividing Range. Now, I'm not sure the exact answer on why Brisbane has a lot of metamorphic rock, but I'm imagining that this area had more igneous activity and it's hotter over a long period of time, more pressures as well, more activity, just more geological activity with that Great Dividing Range, and then that's why we have more metamorphic rock. Excellent question. Now, another way I want you to think about volcanoes, I know it's a little bit gross, but I can think of them kind of like a pimple on the Earth's surface. Well, a pimple is caused by inflammation under your skin, which makes like a round bump on your skin. Yeah, ew, I know that's gross, but honestly, it's really similar to how a volcano is made on Earth. There's inflammation under the crust from all the tectonic activity, subduction zones, things like that, and it builds up and it would make this large sort of bump on the Earth's surface, and then eventually it might erupt. Now, I might do a couple of volcanic eruptions at the end. I have about 10 minutes left. I want to talk a bit about soils as well, because soils are really important when we're trying to grow crops, we're trying to build houses. We can actually split up soils in a special way. Over here, I have got some sieves. Now, these have different sort of meshes. I've got a big one at the top, right down to a really small one at the bottom. And you can imagine that we can actually separate soils out by using these sieves. So here, I've got a cup of sand and rocks. Let's just empty that in there. And then I'm going to swirl it around. Swirl, swirl, swirl. Whoa, that was a bit noisy. Now, I don't have to keep swirling all that much, but let's take a look at our different fractions of soil that we got. I'm going to swap to my top-down camera again over this side so we can see what we've got. Now, I'm showing you these soils because it's all part of the rock cycle too. As the rocks are getting churned up by erosion and forming new sedimentary rocks, they break apart, and that's how our soils can change. Now, let's take a look at the top. Of course, we've got our really big rocks there. That's what that mesh caught. Keep going. I've got a couple of smaller pebbles that didn't make it. And then I'm going to Put this right under the camera. Maybe I'll swirl it a little bit more as well for you guys to see. Here we've got a larger grain, and if you look carefully, there's actually some sparkly bits in there. I added a little bit of pyrite there, so I feel like I've struck gold. Now, someone before asked the difference between gold and pyrite. Now, gold and pyrite, they're simply just different minerals made up of different elements at their base level, and they form in different ways as well. Okay, let's look at the next fraction. Oh, it looks like almost all of the sand I added before was actually in here in the middle. This looks like just your regular beach sand. Keep going, keep going. Oh, hang on, there's heaps more sand here, but this one's a lot finer. Now, it's important to know what's inside your soil because that depends on how good it is at holding water. Is there any left? Oh, yes, can you guys see that? It's really, really fine. I don't know, I think we just got one more fraction right at the bottom. There we go. Oh, is there any left at all? I wonder. Oh, there's like a tiny amount of dust. Can you see that getting brought up on the camera? Got a teensy tiny amount of really, really fine dust down there. Looking at what's inside our different soils, that's how we can determine if it's going to be good for our plants, bad for our plants. Sandy things are good at letting through water, but they're also very loose. And so water can make all the sand rush away. It's too much erosion. Clay is also good at holding water, but it can hold it too much. You actually want a big balance between sand, silt, and clay, so we can get our soils excellent for our crops. All right, we're almost at the end. I want to talk more about volcanoes because volcanoes are a result of our tectonic activity. Of course, we have our earthquakes as well, but volcanoes, we can definitely see the effects of the magma coming out from the earth as well. Don't forget to ask some questions. I might have time to answer them right at the very end. Now, I brought up that word viscosity earlier. When we think about volcanoes, it's important to know the viscosity of magma and lava. Viscosity is just referring to the goopiness, so how thick the liquid is. If something is really viscous, really thick, it's like pouring yourself a cup of cold honey. It comes out really slowly, thick and goopy. If it's not very viscous, then it's thin and runny, just like pouring a cup of juice that happens really fast. I have got some viscosity tubes here that can show you how different liquids actually can have different thicknesses. So inside the viscosity tubes, there's some balls at the bottom. Let's zoom up a little bit so we can see. If I flip them like this, then we can have a look at how they are going at different rates. This reminds me of how different lava has different viscosity as well, and this can change the style of volcanic eruption. There are two main types of volcanic eruptions. We have got stratovolcanoes and shield volcanoes. A shield volcano has lots of thin and runny lava that spreads out really fast. We have lots of shield volcanoes in places like Hawaii, and Hawaii is theorized to have been formed by volcanic hotspots as well. So hotspot underneath the tectonic plate, kind of putting up a plume, makes an island, and as the tectonic plate keeps moving, it's going to make more islands on top as well. Now, these volcanoes are often erupting a lot, but they're not all that dangerous because, well, you know it's erupting, so you just don't go over there, okay? So people keep tabs on these shield volcanoes. I actually have a little model here that can kind of demonstrate a little shield volcano for fun. Well, let me ask, hands up if you've ever made a volcano at home for like a science experiment, because honestly, guys, really popular science experiment. I'm going to be using some vinegar and bicarb soda to do a little fun volcano. Now this model here is actually 3D printed of a very famous volcano. If anyone has an idea of a famous volcano, write it in the Q&A. I wonder if anyone knows what this volcano is. Now I will say, in life, this famous volcano was not a shield volcano, it was a stratovolcano. I'll do an eruption of a stratovolcano soon as well. Now first, I've got to add the vinegar. Now let's see. I don't want to spill it, guys. I'm probably going to spill it. That's okay. I'm going to add some vinegar right into the bottom. There we go. Yep, I spilt it. Don't worry. That's why I have the tray there. Science is messy. As long as you clean it up, after, then it's fine. I've got some vinegar in there, and in this cup, I have the bicarb soda. I'm going to add a bit of water to the bicarb soda so it makes like a thick slurry. Stir, 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 stir. I'm going to get a little spoon as well so I can stir that even better. Now, if you're making this again at home, you can do this easily just with a cup, and you get some Play-Doh or some sand to make your volcano. You don't have to get a special 3D printed one like me. My tips are, add a bit of soap, because that'll help trap the carbon dioxide in the reaction, so it makes it look even more bubbly. And of course, you've got to add a bunch of red food coloring so it looks like lava. Whoa, there we go. I've added heaps. Let's mix it up. Mix it up. Oh, that looks like some serious lava. Maybe some more water as well. Mix, mix, mix. Now let's have a look to see if anyone has identified the this special volcano. Oh, Olympus Mons, very good. It's not the right answer, sorry, that was confusing, but I was impressed that you knew that one. Olympus Mons is a really giant volcano on Mars, so that's not even on Earth. Oh, excellent, one of my friends has got it correct. Mount Vesuvius, ancient volcano that erupted and destroyed the cities of Pompeii and Herculaneum. Now, we know a lot about Mount Vesuvius because there's actually first-hand written accounts of people who saw it happen and they wrote it down, and we found the preserved evidence from that. And also, the lava and the ash covered the city so fast it preserved much of the people and the places, so we could actually investigate them, which is why we know so much. All right, guys, let's take a look at what our shield volcano can look like with thin, runny lava. I've got some dinosaurs here as well, just for fun. Okay, are you ready? 3, 2, 1. Oh, there we go. It's starting to bubble and erupt and erupt and erupt. Let's do another eruption because often volcanoes erupt more than once. Add some more there. Oh, it's starting to bubble out and spew lava all down the sides of the mountain. Oh no, RIP, the dinosaurs. They're going extinct. Oh, poor dinosaurs. There we go. Let's do one more buzz. Yeah, that lava is erupting, flowing fast down the sides of the volcano. Now, so often with some volcanic eruptions, it's not just lava that comes out. Sometimes you get superheated gas and also ash and dust, and that stuff can also cause serious damage. You can't really outrun the superheated gas. Don't worry, don't have to live in fear of volcanoes erupting all the time. Geologists are really good at detecting the Earth's activity to see if something will erupt. Now I've got a couple of minutes left. I'm hoping I have time to do one more eruption. This one's going to be a bit tricky because sometimes it can go really high. I'm going to try and trap all those bubbles inside this thing called a film canister. Now, they're really hard to get these days. Maybe your parents still have some lying around, and they might have them at specialty film shops as well. Film canister is something that you used to have to develop your photos in, but these days we just use it for science experiments. Now, I know you can't see exactly what I'm doing. Basically, I'm just adding some bicarb soda to the lid and I'm wetting it a little bit so it makes a paste. Then I'm going to put the vinegar on the other side and then mix the two together. There'll be a pop underneath and hopefully we get a volcano to erupt. That's going to be our stratovolcano. The stratovolcanoes build up pressure over time and then they have those explosive eruptions. Famous stratovolcanoes include Mount Vesuvius, Mount Fuji in Japan, Mount St. Helens in America. If you search some pictures of Mount St. Helens, you can actually find parts of the mountain starting to bulge out before it erupted. Very, very scary. All right, let's add a bit of vinegar to this side. And I've done this experiment many, many times. Sometimes it works beautifully, sometimes it doesn't work at all. Well, that's kind of like volcanoes. They can sometimes threaten to erupt and not erupt, and then they might erupt by surprise. Now I'm going to do it in front here, and I'm actually going to try and trap it with the cup because I have lots of lights on the roof and they could actually damage it. All right, for our final minute, let's see, can we get an eruption? Here we go. It's building up, it's building up. Oh, whoa guys, did you see that? That happened so fast. I'm glad I catched it. sorry, I'm glad I caught it, that had a lot of energy. Now, guys, it looks like we're at the end of our VC today. Thank you so much for coming along, and I hope you have a good rest of Earth Science Week.
Thank you so much for sharing all of that, Amelia. It was absolutely fascinating and a wonderful follow on from our first session this morning. And experiments are always fun. So in our follow-up notes, you'll be getting a link to 200 experiments on the Fizzics Education website, a link to some of the plate tectonics information on the Geoscience Australia website, and how to make that erupting volcano as well. So yeah, a big thank you to Amelia and Fizzics Education, and once again, proudly brought to you by Geoscience Australia. We're not even halfway through. We've got so much more to go. We've got Anne Stowe looking at in their elements, so we'll drill down to the elements that make up some of our rocks and minerals that we've been talking about this morning. So really appreciate everyone joining us, your great questions again, and the fabulous presentation by Amelia from Fizzics Education. Thank you, everyone, and see you soon.